Ever wonder how a chip can fit billions of tiny switches onto something smaller than your fingernail? I mean, we're not talking about carving them with a microscopic chisel, right? So how do they actually do it? The answer is printing. But not with ink. With light. Welcome to photolithography, the reason your smartphone has more computing power than the Apollo guidance computer that sent humans to the moon. And I promise, by the end of this episode, you'll never look at a camera flashed the same way again. So here's the basic idea. A chip is made of many, many layers, each one a complex pattern of wires and transistors. To build those patterns, manufacturers use a process that's basically a super high-tech version of stenciling. You've done that before, right? You put a stencil on a t-shirt, spray paint over it, and the paint only goes through the cutout areas. Photolithography works the same way. Except the spray paint is ultraviolet light, and the stencil is something called a photomask. The photomask is a quartz plate with an opaque chrome pattern on it. That pattern is the blueprint for one layer of the chip, say, the layer that connects certain transistors to each other. The mask is placed above a silicon wafer that's been coated with a light-sensitive material called photoresist. When you shine ultraviolet light through the mask, the light passes through the clear parts and hits the photoresist, changing its chemical structure. Then you wash the wafer with a developer solution, and the exposed photoresist either dissolves away or stays behind, depending on the type you're using. What's left is a perfect copy of the mask pattern, right there on the wafer. Now here's what's interesting. That pattern is then used as a shield for etching or depositing materials. So the photoresist acts like a temporary tattoo. It protects some areas while you remove or add material in others. Once that step is done, you strip off the photoresist, and you've got one layer of your chip built. Then you repeat the whole process for the next layer, and the next, and the next. Some advanced chips need over 80 layers. But precision is everything. Think about it like this. If you're drawing a map of New York City, and your street lines are just a tiny bit off, suddenly Central Park ends up in the Hudson River. On a chip, a misalignment of just a few nanometers, that's billionths of a meter, can turn a working processor into a useless piece of silicon. The machines that do this alignment, called steppers or scanners, are mind-bogglingly accurate. They use lasers to measure position down to the atomic scale, and they align each layer to the one before it with the precision of a landing aircraft hitting a runway that's 1 atom wide. To give you a relatable example, imagine you're trying to take a photo of a penny from a mile away, and you need to capture every single scratch on Lincoln's cheek. That's the kind of resolution we're talking about. In fact, the latest extreme ultraviolet lithography machines, EUV for short, use light with a wavelength of just 13.5 nanometers. That's about 50 times shorter than the wavelength of visible light. And that's how we can print features smaller than the wavelength of the light itself. Now, here's a common misconception I want to clear up. People often think photolithography is like a printer. You just feed in a design and out pops a chip. But it's actually a serial, multi-step dance. Each layer requires its own mask, its own exposure, its own chemical bath, and its own inspection. A single misstep means you scrap the entire wafer, which can cost thousands of dollars. That's why companies like TSMC and ASML invest billions in perfecting this process. It's not just about printing, it's about printing perfectly, every single time. So next time you hear about a company shipping a new chip, or a factory investing in a new lithography machine, you'll know what's really going on. They're printing circuits with light, layer by painstaking layer, at a scale that borders on magic. Next time, we'll get into doping and layers, how we actually build transistors atom by atom, turning plain silicon into the brain of your computer. Subscribe to Taiwan Tech Pulse for more Taiwan Tech 101.